transition matrix, and I will show what their relations are later on. But here I want to point out that I already mentioned earlier is that there is no efficient classical algorithm to do this kind of computation. Like even though in the literature, like this is also a fairly new result in the classical random walk communities, they can construct transition matrix. They can offer random walk on those simplices, high dimensional simplices. But again, this algorithm is not known to be efficient. And the reason is that this matrix is too large, right? And they don't have this, they cannot use interference to cancel out many of the terms. So that's why their convergence is very slow. Okay, once we have, we know how to do that, then we could use this, again, this is the standard steps, quantum singular value transformation to implement this projector onto this Laplacian kernel of Laplacian. Okay, again, so to construct the transition matrix, remember that in our talk that we consider the originated version of it. So now you need to identify what is called the up adjacent, and the other direction is called down adjacent. Here is the definition. So I think I have, let's start from this up adjacent. So this is the notation for up adjacent. So it means that if these two simplices share a common higher dimensional cofaces, then these two simplices are up adjacent. So this is an example. So for 2, 3, and 1, 2, this is up adjacent because they share this coface 1, 2, 3. But if you look at the inverse direction, so for example, 2, 3, and 2, 1, so this is not up adjacent, okay, by our definition. So, and this would create this matters, this orientation matters. And then similarly, we can consider the down adjacents. It means that you look at a dimension, like one smaller dimension, and whether they share if we consider k simplices, then you ask whether they share a common k minus 1 faces. So and this is another example. So 1, 2, 3, 2, 3, 4 share these faces. This is like a two-dimensional faces is an H. Okay. Okay. And then this is the definition for degree. So like a degree for a simplicis for this face, here is 2. So you count, one is red, the other is blue. So once you identify those, then you can write down the transition matrix defined on this simplicis, a transition matrix. So this is the transition matrix that resulting from our definitions. Some of the terms that I did not mention, for example, this theta is called the absorption state. So when you reach this state, it won't go out. So so like the transition probability is always 1, right? In case the normalization terms. Okay. Then once we have this transition matrix, the second step is to just to encode this transition matrix using a quantum walk, right? To a quantum state. And this idea to do that is like it's very similar to the CZD's quantum walk, right? So you can CZD quantum walk tells you approach to encode a Markov chain transition matrix. And we can also do that. So we have slightly different ways to encode this Markov chain transition matrix. And we can show that this is efficient in if it's a clique complex. Okay. So once we have this quantum walk unitary, then we can construct, we can really obtain this, this Laplacian using this equation, right? And this V matrix is really constructed using a quantum walk plus a swap operation between these two large registers. And then, then from this, this is again a jargon, right? This is a jargon in quantum algorithm. So we call this U Dagger swap U a projected unitary encoding of this transition matrix, right? So then once we have V, then we can use quantum singular value transformation on V to kind of like to, the purpose is to create a projector, right? So we use a function that mimic this kind of like step function in a sense. And then in order to get a good error epsilon, then you have to access this quantum walk unitary this many of times. So this part is very standard. Okay, so this slide shows that if it's a clique complex, right, then we can really prepare this unitary, quantum walk unitary efficiently. So the first step is that we have to create a superposition state that encodes the neighborhood relation between two simplices. And there is a method to do this efficiently by Liu, by one of our by our collaborators, and this has been published in QIC, Quantum Information and Computation. And then the next step is to use membership query, membership function to query whether this, these two simplices are in the same homology or not. And again, we could implement this membership function efficiently in our case because the number of neighborhood edges is scaling as n, number of vertices, and so that this implementation is also polynomial in n. Okay. So yeah, so this is a slide to show that we could efficiently construct the quantum walk. Okay, so finally, of course, that you could already apply that to compute this normalized Betti number, and we obtain the same result as those earlier results. So the time complexity depends, its polynomial dependence depends on the number of vertices. So in a sense that we did not improve upon earlier complexity, but we propose a new method using quantum walk, and in my opinion, this is more elegant in a sense. Okay, thank you very much.
Any questions? Please.
Okay, thank you. There is a question, so is there a connection between these Betti numbers and the genus of a topological object?
Sorry, could you repeat again? So what is?
So is there a connection between these Betti numbers and the genus of a topological object?
Between Betti number and genus?
Yes.
Genus. I don't know. I'm sorry, I don't know.
Okay, okay, thank you.
Okay, any other questions? Okay, I want to ask if this idea can be applied to computing other features.
Oh, yes. I think this is a very good question. In our paper, we actually can show following similar steps to implement almost every object that I introduced, boundary operators, cophase, phase, every of these element here. We could have efficient